What's up, guys? Recently I've been taking a dabble in x86 assembly, and uh, uh, since I'm dabbling x86 assembly, I'm also like dabbling some x86 64. Uh, Apparently, I didn't know. So before, when I dabbled in assembly, I I I was focused on x86 64, and I was like looking up some registers, and I was really confused about what the fuck I'm looking at. And as you can see, so this is like a system called table, and before I was I went to this website to learn about the Linux system calls. Apparently it's outdated now, it has been moved to this one. This is not the current one. And I'm gonna like talk about assembly and like what I learned from it. So so I use Linux. If I use the fact page. I use Linux. Here it is. I'm using DevOS, and these are my specs. So I use Linux, and since I use Linux, I need to find assembly instructions or system calls for the Linux kernel in assembly, and that's why I have this website opened. Now I thought about it, and in this video I'm gonna dabble. Keep saying dabble. In this video I'm gonna use x86 x86 assembly instead of x86 64, since I mean there's really I think x86 is just more awesome to learn as a beginner, and then learning x86 64 will become more understanding once you find the fun in x86 programming. Because before, when I started learning assembly, I did x86 64 and I didn't understand what the fuck RX was, RDI, RXI, RDX. Like if these are like general purpose registers that follow continuously, like the way x86, you can see it, the way x86 handle it, EAX, EBF, it just seems like there's just more structure. And you can see like the equivalence between x86 and 64. EAX is RAX, EBX is RDI, ECX is RZI. So uh, yeah. So let's get started. Stop assembly. So we're going to first open up a file, or well, we're not gonna open up. We're gonna create a file called hello world assembly. I'm obviously gonna take a hello world function. I'll let the music play. So in assembly, so in C and C++, or maybe in like even like Java or any other programming language, except maybe Python or a language like that, there's like an main function, like an entry function that you begin calling the functions in the program. So in assembly, that exists as well. It's called a start. So we're gonna have we're gonna define global start. We got NASA mode. So I had NASA mode, the way I got the NASA syntax. As you can see that. So I got the NASA systems. I got the NASA syntax because I think Emacs comes with like assembly in an assembly mode whenever you open an ASM file, and it's like it's you're putting assembly. And I think the way it formats it is it formats it in GNU assembly, but I'm using NASA. And I don't like the GNU assembly syntax. Well, not syntax, but the way that Emacs just the way like handles it. So I downloaded a package called NASA mode. That way I have it like this. Unimportant, but I just figure, you know, if you're interested how is it I'm formatting it this way, there you go. That's how. So now that we define start, which is gonna be our entry, which is our entry function, we can start calling system calls. So since we're using x86 assembly, we're gonna use EAX, EBX, ECX. So we're gonna use these registers. And as you can see, these registers You can see a line with like, so arc0 is gonna be arc0 here. So if we're gonna ever like mess with arc0, we're gonna call EBX. So and whatever value EBX is gonna be assigned to whatever the argument 0 is for that system. So since we're doing x86 64 assembly, sorry, x86 assembly, we cannot do these tables. This is for x86 64. x86 64 is compatible with x86, but the instruction calls for x86 and x86 64 registers, they're they're way different, at least in Linux. If you're in Windows, again, if you're in Windows, I'm sorry to say I'm doing this in Linux. I think I said that before. I'm not sure. Uh, Forgot. So we gotta find the one that talks about x86, because you'll see. So we go down the bottom, x86. Here we go. You can see the first system call is actually exit, and we see in x86 64 the first system call is write. Big difference. Big difference. There's also another big difference. Now, if you want my honest opinion, if you're gonna do like any meaningful work, if you wanna learn assembly, I recommend x86. If you're ever gonna like do like meaningful stuff in assembly, I think x86 64 is the way to go. Not just because it's popular. Well, probably because it is popular, but it's also it has more safer calls from what I've read. And now I'll get to it. So the way we do is we gotta call. We gotta like mention what is it that what system call we're calling, and the system call it calls from EAX. So whatever value EAX is whatever system call it calls. So let's say we want to exit. So we're gonna do 1. Then the following, the argument 0 is gonna be EBX. So our EBX is gonna be the error code we exit. So let's do something like 3, right? And what this is basically just, if you're in a main function, this is basically this. Return 3. That's all this is. This is basically this. And then what we do is we then do syscall. That's what we would do if we're compiling x86 64, but in x86 you need to call int. So int, it doesn't mean what you think it means. Int in assembly means interrupt. So we gotta do the we just gotta put the move. I forgot about that. So we applied these values. This is basically just EX equals 1. That's basically what move technically does. So we gotta call interrupt x80. And x80 in assembly, it says int module. I don't know how correct this is, but int instruction basically cause like an interrupt, and we call an interrupt to x80. We're basically calling an interrupt to the kernel, so the kernel like does something. Again, like this is just me talking on my ass. Like this is just me like talking about x86 assembly and what I learned, and just put it in video form. And if you're interested, like say your opinion on just hear me out. So in x80 that's like it's basically system syscall, but for x86, which is 32-bit. And this calls like it like sends like an interrupt to the kernel, and the kernel like does like something and then like sends it back depending on what you want it to write. Apparently this is very inefficient and it has a lot of CPU overhead, which is why syscall is much preferred if you're programming x86 64. Because if you call this, it's just it will only work when this won't work in x86 64, and syscall won't work that well with x86 code. So we call that, what we can do now is we can go here and we can put NASM F since we're so the F flag tells we're telling NASM what output we want. So we want an ALF because that's the binary file the binary and executable file that Linux handles. ALF32, and we put in hello world ASM, and we output a hello world object. There we go. So now that we do that, we need to call LD. Now, what is LD? Then the LD. So LD is the GNU linker. So we need to link our object file to make it be a binary. So we do LD. We gotta do a -m in order to tell LD what file we're compiling. Because if we do it like this, and we put like the object hello world.o, output hello world. You can see it complains that this is an x80, this is an i30, this is an x86 architecture, not an x86 64, which is the default. So we gotta do M, and then we gotta do i386, I think. We gotta do, there we go. It tells us we gotta do elf i386. Then it compiled. So we run hello world. Nothing happens because we call an exit system call. But it should have exit with returning 3. So we go echo $, question mark. We see, look at that. We got 3 because that's what we return by. So our code is successful. So what we do, like in normal programming, you do like an in main, and then we do like a return 0 if it successfully. It's basically is this. So if we do this, we can compile it like we did. So NASM with an LD, and we run it, and then we you can even see our little arrow didn't change to like a red because it knows it exited it successfully. Because in programming, returning 0 to exit up the program is successfully exiting the program. So we run this because our return call is 0. Perfect. That means it's working. So let's print like a message. I want to keep that. So we need to call that write. So it's gonna be 4. So move EX to 4. And then we gotta check, okay, what's the second argument? I mean, what's the first argument? So we need to pass in a file descriptor. Now, if you don't know what a file descriptor is, I should look it up here. Build this. H. File descriptor. It's the odds. Okay. Man, UniSTD. H. Guys, I'm actually really trying to look it up so I can explain it to you, but it's just a lot of information. So I'm just gonna like give you like a basic rundown of it from memory. So a file descriptor is basically what we call in order to take input, take output, and print out an error. So there's three main file descriptors. I don't know if like they're like the main the only file descriptors, but the one we interact with it mostly. If I'm wrong, so sorry. Again, I'm not an expert. It's just me like talking about it. So file descriptor 0 is our center input. File descriptor 1 is center output. File descriptor 2 is our error. So in C, yeah. Actually, if you want to learn this, learn about the UniSTD.h. So you learn about like do this, learn about UniSTD.h, and learn about the write function in C, and it might help you okay. As you can see, feel this. It might help you learn about file descriptors. Even I think even Windows has file descriptors for center input, center output, center error. Yeah, so we need to specify what center out what file descriptor we want to use. So we want to output a message. So we want to output a message. That means we gotta use the center output file descriptor. Another name for them is the stream. So like the output stream is a center out, the input stream is a center in, and the error stream is the center error. That's another name for the file descriptors. So file descriptor 1 is center out. Build test 1 is center out. So then let's see the starter argument. So we need a constant chart. So we need a buffer to run to memory. And we gotta store that in ECX. So move ECX. So you might imagine it could be something like this. Hello world, and then you can like store hello stores hello world in ECX. I can't. What I have to do is I have to do a move. Sorry. I have to instead put this in like a defined byte, which is essentially like a variable, I think, in assembly. So we give it a name. I want to name a message db, which means defined byte, and then we input what we want this byte to define. So we want to be what was that we wanted to store? We wanted to store hello world. Now you might think, actually, I'm gonna save that. So I can even show you what happens if I say if I run it like this. So exx. Let's see our third argument. The count is how big it is, which is gonna be our edx. So edx 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 13. Look at the length of the edx. So if we run it now, there we go. That's and you can see character constant too long. Keyword data exceeds bounds. It's like a warning. So if we gotta store in like a defined byte. That way it points to like the end of the address, and the end will be this one. Since it's like messing with memory, it's like I guess it's like a safe thing. So we got now something we go now compile successfully. Now we need to run the linker. And then now we call hello world. And you can see, look at that. Hello world. Now you can see it print another byte. That's because my dumbass made this shit too big. So I'm gonna like put like an exclamation point. And you can see hello world. But you can see it has this line, which means it didn't end with a new line. So the way you add a new line is you don't do this. Watch happen when I do this. I gotta like make it 14 so I can fix that out. Uh 15. I only linked it. God damn it. 15. Linked it and then run it. You see, it treats it. It doesn't treat it as a single byte. It treats it separately. See, this means nothing to it. What we gotta do is we gotta append a value to it, and this is where ASCII comes in. So the value we append is gonna be a new line feed, which is 10, or you can do in hexadecimal, which is 0xa. So that means 10. 10. So it's gonna go to hello world, and then at the end, it's gonna add a new line. So let's try that out. Oops. Nazam. Then like it. Then run it. And you can see, boom, new line. Oh, whoops. Again, we get the memory error because it's too big. And there's a fix for that. So we don't gotta worry about it. There you go. Perfect. So how can we get the total length if instead of magically having to type it? There's a way. So we gotta first name it. So I'm gonna name it Len. You can name it whatever you want. You can name it magical only Len. I can name it something like that. And then what I wanted to do is I need to put the equal, and then I gotta put a dollar sign. Now this dollar signs you need to NASM. It basically takes in this address and goes, so it goes to like the end of it, and then I got the minus sign message. I'm gonna put even a section. I learned about section as well. So apparently data holds the sorry, that's not working that well. So data holds like the data for like the specific code, a specific file, and then section text holds like like the main code, like your start code. I'm not that familiar with it, so I just think it works like that. I can also just take this out. I think nothing bad will happen. Anyway, I'm gonna show it in here. So from my understanding, if db is like storing a value in a variable, what equal is it define is like basically a define. So define magic pony landing, and it's gonna define it as $sign minus smg. Now what is $sign minus smg? Well, what is a $sign? $sign is exclusive to NASM. So in like other assembly languages, you probably can't do this. And in NASM, the dollar sign basically points to like the end of this address. So let me show you it in color. I don't know why it's so small. So we have here our hello world. Uh, uh, um, empty, which is a space. Where, oh, oh, I'm sorry for the bad drawing. I'm not good. World summation point. And then like I think we have the null terminator here. Well, no, we have that new line here. And then like we have like another one where it's like the null terminator. I think it's like that. So what this does is that the dollar sign goes to the end. This is dollar sign. And then we do minus message. What it does is message points to the beginning. The message is at the beginning. So this is close to C, where in C you have a char pointer message equals hello world message. So this pointer points at the beginning of the string, and it reads this whole string until it touches a null terminator. So this is basically what message is doing. And so if we do dollar sign, so we got the end, and we do minus message, what we're doing is we're counting backwards until we reach like the beginning, until we reach message. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14. So we went back 14 in order to get to the first character. That means that it's gonna be 14. So go like magic pony Lenny. As you can see, it prints it out. So assembly is pretty cool. That's what we're learning. I'm gonna like quickly uh convert this into into x86 so you can like spot like the difference and and you can see like the difference with it. So to convert this, I'm gonna like just fully skip it. Fast forward, I mean. Exit system call for x86 64 is 60. So this is basically the way x86 it will be if it's on x86 64. So in x86 64, our registers are racks. These are our general purpose registers, and then we invoke syscall, which is the way we call x86 64 system calls. Again, maybe it's probably gonna be different Windows, but it's how it is in assembly. And in here we call an exit, just a call exit, and we're gonna return with error code, which we can see error code is argument 0, which is RDI in x86 4. So we're gonna call it with 0. So we run it. So instead of doing NASM ALF32, you can see we cannot do it. It doesn't support it. We gotta take that output 64. There you go. Now it compiles. Well, now it like assembles it. NASM is an assembler, so NASM assembles our assembly code into an object file. Then we link that object file into a binary executable. So we can take this flag away, since by default handle LD has x86 64. Compiles it, and it links it, and then now we got our program, and there we go. And it's much better to use syscalls and do it this way. But yeah, that's what I learned. I thought it's pretty cool. I hope you guys enjoy. Holy shit, it's about to be 3 a.m. I need to go to bed.